character of the Magellanic Clouds. This has been a huge mystery since the Age of Discovery. By the 17th century, 100 years after Magellan's expedition circumnavigated the globe, Europe was producing numerous star charts of the southern hemisphere. The constellations were pictured as various creatures: a flying fish, a chameleon, a resplendent peacock, a big-billed toucan. The constellations all had exotic names. And then there was Nubecula Major, Latin for large cloud, meaning the large Magellanic Cloud. That was paired with Nubecula Minor, or small cloud, the small Magellanic Cloud. Since they moved together with the stars, they were clearly no earthly clouds. They were heavenly bodies. But exactly what they were remained a mystery. The first detailed research into the Magellanic Clouds began in the 1830s. To conduct research into stars of the southern hemisphere, England had established a royal observatory at the Cape of Good Hope in southernmost Africa. Astronomer John Herschel worked there for over 4 years. He pioneered the study of celestial objects in the southern hemisphere. In 1847, Herschel published his findings in a 450-page report. This is the catalog of objects Herschel found in the Magellanic Clouds. Some 1,000 items are listed. There are numerous records of nebulae and star clusters, similar to those visible within the Milky Way galaxy. Herschel clearly thought of the Magellanic Clouds as constituting a galaxy. At the time, most astronomers thought that all celestial bodies lay within the disk of our own Milky Way. Herschel thought that these rather indistinct and nebulous objects must be extragalactic celestial bodies. To prove that, however, one would have to calculate the distance to the Magellanic Clouds. Alas, Herschel did not possess the means to do that. Are the Magellanic Clouds inside the Milky Way or outside? An epoch-making discovery at Harvard University finally solved the riddle. The crucial evidence was supplied by photographic plates stored here. This is the world's largest archive of astronomical photographs.
As you can see, we have cabinet after cabinet, many plates, 525,000 plates in this collection. That's 25% of the world's total of astronomical photographs just in this collection. And what is remarkable about that is that it covers more than 100 years of time, from 1885 to 1989, and we began photographing the southern skies early in the 1880s, so that the Magellanic Clouds are covered from that early time.
These photographic glass plates recorded light from the stars over long periods of exposure. They enabled astronomers to capture not only what Herschel could see directly, but even far dimmer stars in the nebulae. Around the turn of the 20th century, the data etched on these glass plates were processed by a team of female analysts. The position and brightness of every single star were meticulously recorded. The analysts were actively seeking variable stars, a popular quarry at the time. Variable stars are stars whose brightness fluctuates. Of particular interest were those whose brightness fluctuated in regular periods.
This was one of the very old ones.
This type of star could help prove whether the Magellanic Clouds lay inside or outside the Milky Way.
With the,
Wow, it's a 240-minute exposure.
Here we have a glass plate of the small Magellanic Cloud, a long exposure which is taken. Some of the stars will be variable stars, but you get them at only one moment on this plate. So this is a negative plate, and we also can then make from one of these plates a positive plate. And this one can then be used as a master. When you put them on top of each other,
Superimposing an image of a given area on top of another taken at a different time reveals any change. If the star's brightness is constant, it should be a perfect match. What happens when the brightness changes? Since brightness is translated optically as size, any variability is immediately apparent. This comparative method, done plate by plate, is a way of detecting which stars are variable. One of Harvard's female star analysts was Henrietta Leavitt, an astronomer later recognized for her analyses of variable stars. This is one of the photographic plates of the Magellanic Clouds that Leavitt analyzed. Out of 100,000 stars recorded on a single plate, she endeavored to identify the variable ones. Harvard still has her handwritten logbook. She assigned numbers to each variable star, comparing readings at fixed intervals and determining the periodicity of its variations in brightness. To prevent any mistaken attributions among the countless stars in the sky, she drew detailed star charts. After 4 years of research, Leavitt published her study of 1,777 variable stars in the Magellanic Clouds. In the course of compiling these data, she made a vital discovery. She noticed that variable stars in the Magellanic Clouds with the same period had the same brightness, or luminosity. Compared with variable stars of the same periodicity within the Milky Way, the ones in the Magellanic Clouds appeared fainter. The fainter the star, the farther away it must be. In the late 1920s, after Leavitt had passed away, detailed analyses revealed that the Magellanic Clouds lie far outside the Milky Way. Precise observations determined that the Magellanic Clouds are 200,000 light-years away. That's twice the diameter of the entire Milky Way. the Magellanic Clouds were definitely other galaxies lying outside the Milky Way. A large telescope subsequently revealed a deep relationship between the Milky Way and the Magellanic Clouds. This is the 2.5-meter Hooker telescope at Mount Wilson. This telescope enabled measurement of the distances to many galaxies outside our own. It revealed features of the Magellanic Clouds that differentiated them definitively from other galaxies. This is the galactic distribution, as currently understood. The two Magellanic Clouds lie approximately 200,000 light-years away from our own Milky Way. The larger one is approximately 1/10 the size of our galaxy. The nearest spiral galaxy to our own Milky Way is the Andromeda Galaxy, some 2.3 million light-years away. That's 10 times farther away than the Magellanic Clouds. So the Magellanic Clouds are two small galaxies very near our own. Edwin Hubble, the leading astronomer of his day, described the Magellanic System thus: the cloud is an independent stellar system and a close neighbor, actually a satellite, of the galactic system. A satellite is a space object that is gravitationally attracted to another and orbits it, as the Moon does the Earth. Hubble thought that the Magellanic Clouds similarly orbit the Milky Way galaxy. This concept of a satellite galaxy eventually became the standard view among astronomers. A major discovery was made in the southern hemisphere, in Australia. The two Magellanic Clouds together make up a single gigantic space object. The discoverer was an Australian astronomer named Don Mathewson.
If this object I discovered was actually visible, everyone would be astounded. It's an enormous arc of gas stretching right across the sky. In fact, it's more outstanding than the Milky Way galaxy.
Mathewson's starting point was a research paper written by astronomers at Bell Laboratories in the United States. Their measurements of intergalactic radio waves revealed filaments of gas in the skies over the northern hemisphere.
It was a rainy Sunday afternoon, and it was quite late, and I was just turning the pages of an astrophysical journal. I plotted their filament of gas, this sausage of gas, and I thought, well, let's extend that sausage a little bit, let's blow it up a little bit. So I drew a line on this polar graph paper, and I thought, gee, it passes through the large and small Magellanic Cloud.
The line Mathewson extended into the southern hemisphere from the mystery gas mentioned in the article went right between the Magellanic Clouds. And Australia had a radio telescope well suited to confirming the presence or absence of gases. It was the Parkes Observatory. Mathewson couldn't contain his excitement. he telephoned the observatory right away. The very next morning, Mathewson jumped into his car and drove to the observatory. The director had told him that the telescope would be offline for maintenance that day, so Mathewson thought that at night there might be a chance for some brief observations. It took him 4 hours to drive to the park's observatory. At the time, this giant 64-meter diameter parabolic antenna made Parkes the largest radio telescope in the southern hemisphere. When Mathewson arrived, he asked the maintenance workers if he might borrow some time on the telescope.
So all the memories come flooding back, because it was the most emotionally charged episode in my life, really, the discovery of the Magellanic Stream.
Past 10 p.m. It was only after the maintenance staff had left for a late supper that Mathewson was able to use the telescope.
Had it all plotted out, what I thought would happen. But of course in science things never happen the way you want it to. Nature is a very, is a teaser. It teases you and then all of a sudden drops you flat on your face. But tonight was completely different. For the rest of the 3 or 4 hours that it took, every position that I looked at with the telescope came out to be the right velocity and the right intensity.
When the telescope was pointed along the extrapolated path of the gas stream first noticed in the northern hemisphere, further traces of gas were found along the way. The gas trail seemed to be headed for the Magellanic Clouds. That's how Mathewson was the first in the world to actually establish a link between the gas trail and the Magellanic Clouds. Subsequent detailed observations confirmed that their distributions were aligned. This intergalactic belt of gas was named the Magellanic Stream. The Magellanic Stream is an extension of the same nebulae spotted by Ferdinand Magellan. It's a huge belt of gas, stretched out as if to curve around the Milky Way galaxy. It's 1 million light-years in length. That's 10 times the diameter of the Milky Way. Like the contrail of a jet plane, the Magellanic Stream is proof that the Magellanic Clouds have passed that way. The gas is distributed as if it were encircling the Milky Way. So astronomers believe that the Magellanic Clouds are spewing out gas as they orbit our galaxy. The Magellanic Clouds, galaxies with a gas trail longer than the diameter of our own galaxy. To people of the northern hemisphere, the night sky of the southern hemisphere presents a strange spectacle. There's the constellation Orion. But it's upside down. And the Milky Way looks huge. The exceptionally bright area is our galaxy's nucleus. In the southern hemisphere, the mysteries of the universe seem all the closer. This is Santiago, the capital of Chile. It's surrounded by 5,000-meter-high mountains. Still bearing traces of its Spanish colonial past, Santiago is today at the forefront of astronomical research. On the way to a green grocer's in a new part of town.
Hola. Gracias.
The shopper is Valentin Ivanov, an astronomer who was born in Bulgaria. Recently, he has been analyzing observations of the Magellanic Clouds made with one of the world's most advanced telescopes. He is affiliated with the European Southern Observatory, known as ESO. ESO has established 3 observatories in Chile from which to survey the stars of the southern hemisphere. With his telescopic observations, Ivanov has been creating the most detailed picture yet of the Magellanic Clouds.
VISTA is one of the newest projects of ESO, and it aims at creating large uniform maps of the sky. These are called surveys. One of the most important surveys that this telescope is producing now is the survey of the Magellanic Clouds, these green squares over here.
To produce a complete map of the Magellanic Clouds, Ivanov spends a total of 1/3 of every year at a mountaintop observatory. He has already taken over 100 of these trips. His destination is about 1,000 kilometers north of Santiago. It's in an arid zone that sees less than 10 millimeters of precipitation annually. This is the European Southern Observatory's largest site. Seven telescopes are located on the mountaintop here, at an elevation of some 2,600 meters. This is the one Ivanov uses. It's a 4-meter aperture telescope called VISTA. Installation was completed toward the end of 2009. Its technology is cutting edge.
VISTA is a special purpose-built telescope. Unlike other ESO telescopes, VISTA is designed to cover extremely large field of view in a single pointing. The field of view of VISTA is about degree by degree and a half.
How does VISTA compare in this regard to the Hubble Space Telescope? VISTA's field of view is about 500 times greater than Hubble's. In a single pointing, VISTA can take in a region much broader than a full moon. Ivanov and his VISTA team are attempting an exhaustive survey of the entire region containing both the small and large Magellanic Clouds and the bridge linking them. It's sundown. VISTA can now be engaged. In the control room, Ivanov will conduct observations all night long. The display shows stars within the Magellanic Cloud system.
The VISTA Magellanic Cloud Survey already completed a number of tiles, and the data are publicly available. This data contain a lot of interesting objects, like this giant H2 region called Tarantula.
The Tarantula Nebula is an expanse of gas located within the Large Magellanic Cloud. It's 1,000 light-years across. Its name derives from the hairy, spidery appearance of its gases.
This image that we see here actually is built from 3 different images, each of them in the near infrared. The advantage of the near infrared and the advantage of the kind of data that VISTA delivers to us is that we can actually see through the dust. If you look at this area on the sky in the optical, you'll see almost no stars because the dust and that absorbs the optical light much more than the infrared light.
VISTA captured this image of the Tarantula Nebula. Compare it to an optical image showing ordinary visible light. It's clear that the VISTA image reveals the stars hidden beyond the gas and dust. The Large Magellanic Cloud is said to contain as many as 20 billion stars. VISTA captures them in stunning detail. Innumerable stars, nebulae, star clusters, countless points of light beyond the reach of ordinary optical telescopes, rendered here vividly and distinctly. VISTA is continuing to survey the Magellanic Clouds at a level of detail unmatched by any other telescope. The Hubble Space Telescope has shown us how different in shape as well the Magellanic Clouds are from our own Milky Way galaxy. This nebula, in a remote part of the Large Magellanic Cloud, shines with extraordinary luminosity. It's gigantic, more than 30 times the size of the Great Orion Nebula. And out of the dark gas and dust, it is birthing countless new stars. One region in the Large Magellanic Cloud is giving birth to more stars than any other region in the Milky Way. Here is just one portion. Newly born stars illuminate the surrounding gas. It looks like a cocoon. Here, an accretion of gas and dust is displayed in silhouette, lit from behind by young stars. The largest mass looks like a seahorse. It's a huge object, some 20 light-years in length. The Small Magellanic Cloud also boasts magnificent nebulae and star clusters. The explosive birth of 100,000 stars. The energy they put out is said to be 60 times that of the Great Orion Nebula. or look at the outskirts of the small Magellanic Cloud. Innumerable young stars, born all in a group. And this sparkling, multicolored, open cluster has been called the Jewels of Magellan. Even today, the Magellanic Clouds are far more prolific than the Milky Way in the production of new stars. The Magellanic Clouds had been thought to be orbiting the Milky Way. But recently, a great discovery was made in that regard. The discovery was made by Roland van der Merel. Van der Merel spent 4 years directing observations of the Milky Way by the Hubble Space Telescope. His goal was to determine the mass of our galaxy, and he found a way to use the Magellanic Clouds to do so.
We thought that if we could measure exactly how the clouds are moving in the sideways direction, we could learn more about the mass of the Milky Way and about the distribution of the mass in the Milky Way.
Van der Merel's group thus observed the Magellanic Clouds directly in order to ascertain the speed of that sideways motion relative to the Milky Way. As a reference point, they chose to use a quasar, celestial bodies that are very far away and so essentially motionless. By using a quasar located beyond the Magellanic Clouds, as seen from Earth, they could measure the cloud's relative motion. They pointed the Hubble Space Telescope in that direction. The anticipated motion of the Magellanic Clouds was minute. It is the equivalent of observing a 1 millimeter movement from 100 kilometers away. That was close to the limit of Hubble's powers of resolution.
And then if you try this with a telescope on Earth, you run into several realistic problems with telescopes on Earth. For example, telescopes are subject to gravity. As the telescope moves, the gravity on the telescope is different, and the instrument distorts a little bit. And you see this in your images.
The observations with Hubble continued for 4 years.
Now, we cannot actually measure the motions of stars in the Magellanic.
Van der Merel's group succeeded in obtaining data on 25 of the regions into which the Magellanic Clouds had been divided. After analyzing the results for a full year, they calculated that the Magellanic Clouds are moving at an incredible 378 kilometers per second, 1.36 million kilometers per hour. This was 300,000 kilometers per hour faster than anticipated.
Initially, we were just very happy we were getting any results out that said, hey, we can actually measure the motion of the Magellanic Clouds. So that was our initial excitement for quite a while. And it was clear we were doing it better than anyone else had done it before, but it wasn't immediately obvious what we were learning.
To extract meaning from these speed calculations, computer simulations were conducted of the relative motion of the Milky Way galaxy and the Magellanic Clouds. The simulations were carried out at Harvard University. The movements of the Magellanic Clouds were minutely calculated, using the latest data on the size and mass of the Milky Way. This is the result. Contrary to expectations, the Magellanic Clouds do not orbit the Milky Way. Assuming the Milky Way is not unnaturally massive, the Magellanic Clouds will eventually fly off into deep space.
I basically computed things like the escape speed, which refers to the speed that an object would need to have to escape the potential of the Milky Way at its distance, at separation from the Milky Way. And for the basic model that I had initially started off with for the Milky Way, the LMC was sitting at the escape speed. So the orbit couldn't be anywhere close to what we thought before.
So it was very normal for people to think for years that the Magellanic Clouds had been going around the Milky Way many times. Cortina realized that that couldn't be at that speed. They were going too fast. They were basically flying away from the Milky Way too fast, which means that probably they were just coming into the Milky Way for the very first time. And this was a very revolutionary thought.
So the Magellanic Clouds are not satellite galaxies of the Milky Way after all. They are visitors from afar, merely enjoying a chance encounter with our own galaxy. In a few billion years, they are fated to disappear into the furthest reaches of space, never to return. The true nature of the Magellanic Clouds is gradually emerging, and astronomical observations indicate that the clouds hold a key to understanding what the universe looked like right after the Big Bang. Paul Crowther is one of the scientists fascinated by the Magellanic Clouds. For 15 years, he's been studying one of the cloud's features in particular. What's attracted his attention is the Tarantula Nebula. At its center, there's a place estimated to shine with the luminosity of 100 million of our suns. R136 is its scientific designation. It was thought to contain a mystery object. Crowther set out to find out what that was. He conducted his observations with what's called the VLT, or Very Large Telescope, located in Chile. He pointed the VLT and its 8.2-meter diameter mirrors straight at R136 in the middle of the Magellanic Clouds. This is the very center of R136. The detailed view provided by the VLT reveals that what looked like one bright clump at its center is comprised of many stars, the brightest of which has been designated R136A1. With a luminosity of 10 million suns, it is, so far as we now know, the brightest star in the universe. Crowther performed a spectral analysis of its light.
The spectrum is kind of like the fingerprint of an object. It tells us what it's made of, it tells us how hot the gas is in the star. And so this actually is an infrared spectrum taken with a very large telescope of R136A1, and it reveals the presence of, for example, this is a line of helium-2, ionized helium, and this means the star is incredibly hot.
Thanks to this analysis, Crowther was able to start profiling his mystery object. This is how Crowther envisions R136A1 in the center of the Tarantula Nebula. With surface temperatures reaching 55,000 degrees Celsius, it burns bright blue. When it was born, it had the mass of 300 of our suns. To date, nothing comparable has been found in the Milky Way. These first-generation stars of the early universe, born right after the Big Bang, were unlike most of the stars we see today. They were formed directly out of hydrogen and helium gases, and they were all blue giants. In the Magellanic Clouds, there are many such stars. The Hubble Space Telescope has captured a number of ancient galaxies that contain these blue giant stars. All these galaxies are more than 13 billion light-years away. So what we see now is how they looked 13 billion years ago. In other words, just moments after the universe was born. Ancient galaxies, glowing bright blue. The sheer number of blue giant stars, similar to the one Crowther has been studying, is enough to impart a blue color to the galaxy as a whole. These galaxies, born just after the creation of the universe, are a mere tenth the size of the Milky Way and have irregular shapes. In size and shape, they resemble the Magellanic Clouds. That is why scientists believe that studying the Magellanic Clouds will provide insights into the evolution of our own galaxy.
Well, so the interesting thing here is that we've learned a lot about structure formation in the universe over the years, and in particular, what has been learned is that structure forms by smaller units coming together. So if you're a big galaxy like the Milky Way, you really started out as lots of little clumps that fell together over time.
One scenario for the growth of the galaxy would go as follows. In the earliest stage of the universe, there were only small, irregular galaxies like the Magellanic Clouds. These small galaxies collided and merged repeatedly. In this way, so the theory goes, over the course of billions of years, larger galaxies like our Milky Way were formed. Van der Merel believes that the Magellanic Clouds are in fact holdovers from the earliest days of the universe, small galaxies that only now are brushing past our own larger galaxy.
In the early universe, soon after the Big Bang, we believe this happened all the time. There were bits and pieces of galaxies falling together to form the first real galaxies that then later grew over time. Nowadays, in our current universe, this is actually a pretty rare occurrence. So the fact that we're seeing Magellanic Clouds pass the Milky Way right now is very unusual at some level, but it really gives us a glimpse of what the universe was like more typically when it was much younger, when galaxies were falling onto each other and merging together all the time.
The Magellanic Clouds had been thought of as satellite galaxies. But it turns out that they are actually leftovers from the very beginnings of the universe. Small galaxies linked together, spewing a plume of gases behind them as they rush past us. At the Vista Telescope in Chile, observations of the Magellanic Clouds are ongoing. The detailed mapping of the Magellanic Clouds, based on the Vista surveys, is expected to be completed in 2017.
Vista is continuing the observations of the Magellanic Clouds, and we are extremely lucky to have this exciting and mysterious galaxy next to us, because it has been a wonderful playground for astronomers for more than a century now, couple of centuries, and I'm sure it will help us to reveal many more secrets.
The origins of the universe, the birth of the galaxies. These are the mysteries to which the Magellanic Clouds hold the keys. As humanity peers into the southern night skies, that quest will continue. Are the Magellanic Clouds inside the Milky Way or outside? An epoch-making discovery at Harvard University finally solved the riddle. The crucial evidence was supplied by photographic plates stored here. This is the world's largest archive of astronomical photographs.
As you can see, we have cabinet after cabinet, many plates, 525,000 plates in this collection. That's 25% of the world's total of astronomical photographs just in this collection. And what is remarkable about that is that it covers more than 100 years of time, from 1885 to 1989, and we began photographing the southern skies early in the 1880s, so that the Magellanic Clouds are covered from that early time.
This is the catalog of objects Herschel found in the Magellanic Clouds. Some 1,000 items are listed. There are numerous records of nebulae and star clusters, similar to those visible within the Milky Way galaxy. Herschel clearly thought of the Magellanic Clouds as constituting a galaxy. At the time, most astronomers thought that all celestial bodies lay within the disk of our own Milky Way. Herschel thought that these rather indistinct and nebulous objects must be extragalactic celestial bodies. To prove that, however, one would have to calculate the distance to the Magellanic Clouds. Alas, Herschel did not possess the means to do that. These photographic glass plates recorded light from the stars over long periods of exposure. They enabled astronomers to capture not only what Herschel could see directly, but even far dimmer stars in the nebulae. Around the turn of the 20th century, the data etched on these glass plates were processed by a team of female analysts. The position and brightness of every single star were meticulously recorded. The analysts were actively seeking variable stars, a popular quarry at the time. Variable stars are stars whose brightness fluctuates. Of particular interest were those whose brightness fluctuated in regular periods.
This was one of the very old ones.
Macula Minor, or small cloud, the small Magellanic Cloud. Since they moved together with the stars, they were clearly no earthly clouds. They were heavenly bodies. But exactly what they were remained a mystery. The first detailed research into the Magellanic Clouds began in the 1830s. To conduct research into stars of the southern hemisphere, England had established a royal observatory at the Cape of Good Hope in southernmost Africa. Astronomer John Herschel worked there for over 4 years. He pioneered the study of celestial objects in the southern hemisphere. In 1847, Herschel published his findings in a 450-page report. Character of the Magellanic Clouds. This has been a huge mystery since the Age of Discovery. By the 17th century, 100 years after Magellan's expedition circumnavigated the globe, Europe was producing numerous star charts of the southern hemisphere. The constellations were pictured as various creatures: a flying fish, a chameleon, a resplendent peacock, a big-billed toucan. The constellations all had exotic names. And then there was Nubecula Major, Latin for large cloud, meaning the large Magellanic Cloud. That was paired with Nubecula